Okay, so in the previous video we were talking about this graph, and we got into a whole business of basically formulas and angles and so on and so forth. So we got into we got to the basically x is equal to 90 degrees, and basically we calculated basically the outputs of the function f of x is equal to cot x. We said that at x is very close to for x is very close to basically, this is the y-axis, so this is very close to 0, then the output of the function was very large. For x is equal to 45 degrees, or basically pi by 4, the x was equal to so this is basically, so over here at 0 you are undefined, at 180 degrees you are undefined, so this is 90 degrees or pi by 2, so this is pi by 4, right? So when x is equal to, I remember that we got somehow into 135 degrees, meaning that we got over here, so that is 90 plus 45, this is 135 degrees. So when you get to 145 degrees, you want to calculate the cot of 135 degrees, which is the same thing as cos of 135 degrees over the sine of 135 degrees. And basically we argued that the cos of 135 degrees is negative square root of 2 by 2, and sine of 135 degrees is square root of 2 by 2. So negative square root of 2 by 2 is negative square root of 2 by 2 by square root of 2 by 2, which is going to give you a negative 1. That means that the output of the function at this point is going to be negative 1. And then when you get very close to inputs, like for example, when you get very close to the inputs, like for example here, which is 180 degrees, very close to 180 degrees, you want to calculate the cos over the sine of, for example, some value, like for example 175 degrees, and sine of 175 degrees, right? So you can see that the sine of 175 degrees is some angle very close to 180, and it's very close to 0, because this height is very, very close to 0, which means that it's some value, for example, like 0.00001 or 0.1 basically. And the cos of 175 degrees is some value which is very close to negative 1, which is something like, for example, negative 0.00, negative 0.9999, and so on, and 9, for example. Now if I multiply these, the numerator and denominator, by a factor of a million, I will get basically, let's put another 9 over here, I will get something like negative 999,999, something like that, right? Which means that at very close to 180 degrees, the output of the function is very, very small, something like negative 999,999, which is somewhere over here, which means that the function is going to be something like this, right? So the function is basically something like this. And then, as we saw earlier, the function does the exact same thing in all of these periods, which means that this function would look exactly like this. And you have the same thing over here, right? You have the same thing over here, and you have the same thing. You have the same thing over here. So that is the graph of the function f of x is equal to cot x. So what's important here is to note that basically all the multiples of pi are excluded from the domain of the function, and exactly at those points you get these vertical asymptotes, right? So the next thing that we have here is basically the graph of the function secant x, the graph of the secant function, right? 240, 246. So in order to draw the graph of the function secant x, so we have the secant function. What basically, in order to draw the graph of this function secant x, you know that is defined as 1 over cos x, meaning that wherever cos of x is equal to 0, of course this function is not defined, and the cos of 0, the cos of x is 0 at the cos of 0 at 0 at over here. Cos is equal to, the value of the cos is equal to 1, and then it keeps decreasing as you increase your angle until you get to 90 degrees. At 90 degrees, cos of 90 degrees becomes 0. Then again over here the values are negative, meaning that it's a very starting from for example angles like, for example, something like, for example, 91 degrees, some angle very close to 90 degrees, the value of the function is a number very close to 0, meaning that you have 0 point, for example, you could say that cos of 91 degrees is the same thing as something like, it's a negative value, and it's something like, for example, 0.000001 or something like that. And we can test that idea as well. And we can write the cos of 91 degrees, as you can see, it's equal to negative 0.017. Of course, it's not that small, but it's approximately negative 0.017, right? So the value of the cos function is very close to 0, but a negative value, and then as you move towards 180 degrees, the value of the cos function decreases and gets to -1 when you are here at 180 degrees. The cos of 180 degrees is equal to -1. And then once you move past 180 degrees, then 181, 182, the value of the cos function starts to get closer and closer to 0, but still a negative value, until you get to 270 degrees. At 270 degrees, the value of the cos becomes 0. So the cos of 270 degrees is equal to 0. And then as you move towards 0 or 360 degrees, then again the value of the cos function will start becomes a positive number and starts increasing until you get to 1 at 360 degrees. which means that as at 90 degrees, at 270 degrees, at these two, basically at these two values, and at all of the multiples of these two angles, or you could say at all the angles coterminal with 90 degrees and 270 degrees, the value of the cos function is going to be equal to 0, right? Which means that I can say that basically cos of x is equal to 0 for all x belonging to the set of for example, or you can say for all x equal to, for example, 2n plus 1 times pi by 2 times pi by 2 n belonging to the set of integers, right? Because if n is an integer, and then if you have basically 2n plus 1 would be, for example, n is equal to 0 would be 2 times 0, which is equal to 0, plus 1 is equal to 1. 1 times pi by 2 is equal to pi by 2. If n is equal to 1, then you have 2 times 1 is equal to 2, plus 1 is equal to 3 pi by 2. If you have n is equal to 2, then you will get 4 plus 1 is equal to 5 pi by 2, and so on and so forth. And then if n is equal to, for example, if n is equal to -1, then you have, then basically x becomes, for example, this is the values of x. X becomes basically 2 times -1 is equal to -2, plus 1 is equal to -2 plus 1 is equal to -1, so that's negative pi by 2. If n is equal to -2, then x becomes -4, -3 pi by 2. And if n is equal to -3, you must get -5 pi by 2, and so on and so forth. And as you can see, these are all odd multiples of pi by 2, which means that you can say that the output of the cos function, the output of the cos function is 0 at all odd multiples of odd multiples of pi by 2, right? Which means that since the cos function is in the denominator here, I have to take out all of the odd multiples of pi by 2 from the domain of this function, because this function is not defined at any of those inputs. Which means that I can write the secant function is a function from basically all of the real numbers, which is, and I have to exclude all of those points from the domain of the function x, such that x is equal to 2n plus 1 times pi by 2, and n is basically, n belongs to the set of integers, and the codomain of the function is the set of real numbers, right? So that is basically the secant function, r minus x, such that x is equal to 2n plus 1 times pi by 2, n belonging to the set of integers, and there is a problem here as well, meaning that there is a problem here as well with the codomain of the function. Okay, so now in order to understand basically the problem with basically what I wrote earlier was that basically secant of the function secant is a function from R, and excluded from R is all the odd multiples of pi by 2 to R, which is actually not the way that the function has been defined. The way that the function has been defined is basically R minus the interval -1 to 1, meaning that all of the basically values from -1 to 1, meaning that take this as -1, take this as 1, all of these values have been excluded from the codomain of the function, but the function does produce basically some values at which are equal to basically 1 and also equal to -1. But then between these two values, the function doesn't generate any output. And so I think for the reason that the function is that the inverse of the function does exist as well, they have defined the function as basically having this codomain. That's the only reason I can think of. Other than that, I don't really know. So now if you take a look at this function on a graph of the function, basically what you will see is that this is the function f of x is equal to secant x. See over here, you see this point, for example, is 0, 1. This point is pi, -1. This point is -pi, -1, meaning that between -1 and +1, there is no output produced by this function all throughout the domain of the function. No matter how much you go towards the infinity or towards -infinity, you will not get any values produced between -1 and 1, and for the same reason they have excluded this from the codomain of the function. So and these asymptotes are exactly at these this odd integers of odd multiples of pi by 2, meaning that, for example, you see that this let me see what we have here. Okay, so you see that for example, this asymptote, this is the y-axis, this axis is the y-axis, this is the x-axis, and this asymptote is at somewhere about 1.7. If you count all of these, basically you see that over here you have 0.5, 1, and 1.5, and this is about 1.7. Now 1.7 is the same thing as pi by 2 approximately. Pi by 2. Pi by 2 is the same thing as what? 3.14 divided by 2, you get something about 1.7. And what that means is that you get an asymptote at 1.7 or at positive pi by 2. You get an asymptote at negative pi by 2, again at this input, which is somewhere about, so you get basically negative pi by 2 and then negative pi, -3 pi by 2, which is this asymptote here. Again, you have pi by 2 and basically pi and 3 pi by 2, which is this asymptote here, and the same thing keeps happening over and over again, right? And well, these are the asymptotes that the function has, and the reason why the function is behaving this way, meaning that it's creating no outputs between -1 and +1, is that suppose that I say that suppose that for the function is secant x is equal to 1 over cos x, right? Now if x is equal to 0, which is basically this point over here, right? At this point 0, the output of the function is 1, right? So what happens is that at x is equal to 0, secant of 0 is equal to 1 over cos 0, and cos 0 is equal to cos 0 is equal to 1. So 1 over 1 is equal to 1, and that's the reason why the function has an ordered pair as 0, 1 at this point over here. This is 0, 1. When you get to basically, now there is this point over here, which is the output of the function as -1, and that is at pi. So at pi, which is between pi by 2 and 3 pi by 2. This asymptote is at pi by 2. This asymptote is at 3 pi by 2, and this point is right exactly between pi by 2 and 3 pi by 2, which becomes pi. And so at pi, the output of the function when x is equal to pi, then secant of pi is equal to 1 over cos pi, and cos pi is equal to -1, which is equal to -1. And as you can see, the output of the function becomes -1. And so on and so forth. You will get basically, again over here you will get the output -1. Over here you will get output +1, and this keeps happening periodically. So for example, over here, this is 0, and this is the y-axis, and this is the x-axis. Over here the function starts at positive infinity, meaning that very close to this asymptote, which is at -pi by 2. The function starts at at positive infinity, decreases all the way up to, you'll get this minimum, or this trough over here at y is equal to 1, and then again the function starts increasing and goes to infinity, tending to the other asymptote. When you get to the next period, the function starts at negative infinity, goes all the way up to -1, and then again keeps decreasing, going to negative infinity. With the next period, again the function starts at positive infinity, comes all the way up to 1, goes to negative infinity, and then it keeps doing the same thing over and over again. And so that's basically what this function does, right? Now the next, I don't really need I don't really feel the need to graph this function. You already saw the graph of the function, and the next function that we have is the cosecant function. The cosecant function. So the cosecant function is basically, cosecant is basically defined as, cosecant x is defined as the reciprocal of the sine function. So 1 divided by sine x is cosecant x, which means that whenever sine of x is equal to 0, which is essentially at this angle and this angle, meaning that at 0 and 2 pi and pi, right? At 0 and 2 pi and pi, then of course, then at these two angles, basically the denominator becomes 0, and of course the cosecant of x would not be defined. So that means that these two have to be taken out or excluded from the domain of the function, which means that I can say that the cosecant as a function is a function from R and exclude from R all x such that x belongs to, such that x is equal to, actually, such that x is equal to basically n times pi, you can say, where n belongs to the set of integers, right? Where n belongs to the set of integers. And then the output of the function is, again, the function happens to produce no outputs at between -1 and 1, and therefore I have to say that basically the codomain of the function is R minus the interval -1, 1, which means that basically so basically the domain is all of the real numbers except for the multiples of pi, and all the multiples of pi, meaning that n belongs to the set of integers, meaning that you have, for example, let's say n is equal to 0, then x is equal to 0 times pi, which is equal to 0, right? And at x is equal to 0, then 1 over sine of 0 is equal to is actually not defined, right? So at this point, basically, at x is equal to 0, you will get a vertical asymptote. If n is equal to 1, then, for example, you will get x is equal to pi, at which point your function would not be defined. You will get a vertical asymptote. At n is equal to 2, your x is equal to 2 pi, at which point the function is not defined. At n is equal to, for example, -1, then x is equal to -pi, at which point the function is not defined either. And at n is equal to -2, then x is equal to -2 pi, at which point again the function is not defined, and so on and so forth, and so on and so forth, right? Now, the function is not producing any outputs between -1 and 1 in this interval, which means that basically the function is, for example, let me take a look at the graph of the function. If you draw the graph of the function cosecant x, you can see that cosecant of x, maybe this is not the cosecant function. I'm not really sure if this is the cosecant function. Let me see. Okay, that basically the cosecant function, which is this red function that you can see here, it has its it has its vertical asymptotes at all the multiples of pi. That means that basically at, for example, at this point, let me see if I can find the function over here, CSC of x. Yes, that is the function. So you can see that at, for example, at x is equal to 0, you'll get a vertical asymptote. At x is equal to about 3.14 or so, about pi. This is supposed to be pi. At pi you get an asymptote. At -pi you get an asymptote. At 2 pi you get an asymptote, and so on and so forth. And then the function is not creating any outputs between -1 and 1, right? And again, you can see the same type of behavior as the secant function, meaning that in each of the periods, basically the function is going from positive infinity to 1 to positive infinity. next period negative infinity to negative 1 to negative infinity, next period positive 1 to positive infinity to positive 1 to positive infinity, and then again negative, and so on and so forth, right? So what that means is that what this function is, again, not creating any values here. For example, at x is equal to pi by 2, let's see what happens at x is equal to pi by 2. When x is equal to pi by 2, then cosecant of pi by 2 is equal to 1 over sine pi by 2. Now sine pi by 2 is equal to 1, so that's 1 over 1, which is equal to 1, right? Now basically the next period of the function, the vertical asymptote is at pi, and then you have 2 pi, so between pi and 2 pi you have 3 pi by 2, right? So 3 pi by 2 means that at 3 pi, let's see what happens at 3 pi by 2. So when x is equal to 3 pi by 2, then cosecant of 3 pi by 2 is equal to 1 over sine of 3 pi by 2, which is equal to 1 over negative 1, which is equal to negative 1. So you see the function, the output goes from 1 to negative 1, and so on and so forth. Which means that the output of the function here is at 1, here is at negative 1, and, well, that's basically the function behaves, right? So you can say that then the cosecant function, the domain is R minus the set of all x's such that x is equal to n pi and n is equal to n belongs to the set of integers 2, and the codomain of the function is R minus negative 1 to 1. That's basically all that we have here, right? Okay, and there is one more thing that I wanted to show you, and that is basically the difference between the cosecant function and the secant function. Alright, I wanted to know it was actually over here. Okay, so you can see that the cosecant function is actually this red function over here, right? And the secant function is this blue function over here. And the only difference between the cosecant function and the secant function is that the whole function is kind of misplaced all throughout the domain of the basically, for example, you can say that, for example, the cosecant function relative to the secant function is misplaced throughout the whole domain of the function by, for example, by a measure of pi by 2, because the cosecant function over here, you have basically this point over here is pi by 2, and so the function, as you can see, has been transformed or basically moved to the, you can say, moved to the right with respect to the secant function by pi by 2 units, as you can see here. So it's basically, I mean, you can basically say that they are the exact same functions, meaning that the codomains are exactly the same, but basically where the vertical asymptotes occur, of course, are different, meaning that in the case of the cosecant function, for example, the y-axis is the vertical asymptote. But then in the case of the secant function, the vertical axis again has moved by pi by 2 units. And so you need to actually keep this in mind in case you want to use any of these two functions for any applications. You know what they naturally do, and of course, you can always move these functions around as you need. For example, I could actually move this function, this cosecant function, move it to the left so that it coincides exactly with the secant function. You see over here, if I write x minus, for example, x minus pi by 2, if I write, which actually did not work. So if I want to move this function, this cosecant function to the left, I have to add pi by 2 to it, because right now they are pi by 2 units apart. Pi divided by 2. And as you can see now, they are exactly the same. They coincide exactly. You can see that right now I have basically pushed this button and the cosecant function is not actually being shown, right? So what you're seeing is the secant function. Now if I actually have the secant function, the cosecant function shown, you can see that you will not be able to see the secant function anymore, although it's actually there, as you can see, right? And the reason that you cannot see the secant function anymore is that because, well, they coincide exactly. And I can, to show you basically what I mean is that I can move it by I can move this, for example, instead of pi by 2 units, I can move it by, for example, pi by 2 would be something about 3.14 or 1.57. I'll just move it as by 1.5. And as you can see now, or 1.4 to see everything. And as you can see right now, the cosecant function is there, and there is a very slight, basically, horizontal difference between the two functions, and the secant function is also there. You see, the secant function is there. If I make this number pi by 2, which is the exact natural difference between the horizontal, basically difference between the two functions, then the two functions will exactly coincide and you will not see the secant function anymore. Which means that, like, if I write here pi divided by 2, you can see that now all that you can see is the cosecant function, and that must be due to the fact that the cosecant function in this graphing calculator is above the secant function. Otherwise, right now, since the two functions are basically do coincide, we would, if the secant function was up here, then all that we would see would be only the blue function, which is the secant function, right? So you can of course move all of these functions around as much as you want or as much as you need, but that's basically how they behave, and that's actually pretty interesting.